In this paper, we introduce several innovative methods to enhance the efficiency of large language models, LLMs. We propose strategies such as multi-query attention and grouped query attention to reduce the key value (kV) cache. By using fewer key and value heads in the attention modules compared to query heads, we significantly decrease the KV's memory usage. This reduction allows for larger batch sizes and improved accelerator utilization. We also introduce a paged memory management scheme to minimize fragmentation of the KV cache. We employ quantization techniques to further decrease the memory consumption of LLMs. We apply rescaling between activations and parameters to eliminate outliers and simplify the quantization process. Matrix multiplications are primarily broken down into 8-bit operations, with a minority of 16-bit operations. We iteratively round weight columns into 3/4 of a bit, and use an activation-aware quantization scheme to compress LLMs to 3/4 of a bit. We also introduce a sparse plus low precision pattern to handle a minor portion of vital weights. We also explore speculative decoding, which aims to execute several decoding steps in parallel, thereby reducing the total number of steps required. We use a smaller draft model to predict several subsequent words, which the LLMs then collectively evaluate and accept if appropriate. Unlike previous works, we leverage the original model to make predictions, eliminating the need for an additional draft model. This approach is more straightforward and integrates seamlessly into existing systems. We introduce truncation sampling schemes to produce high-quality and diverse samples. Different strategies, such as top K sampling, top P sampling, and typical decoding, define the allowed set in various ways. Our proposed typical acceptance scheme aligns with the concept of defining an allowed set to exclude improbable candidates from the sampling process, facilitating more diverse, yet high-quality outputs. We propose the use of MEDUSA heads, additional decoding heads, appended to the last hidden states of the original model. These heads predict the next tokens in the subsequent positions, and consist of a single layer of feed-forward network with a residual connection. They are trained in conjunction with the original backbone model, either by freezing the backbone model, MEDUSA 1, or training it together, MEDUSA 2. MEDUSA heads can be fine-tuned on a single GPU, leveraging the powerful base model's learned representations. We employ a tree-structured attention mechanism to process multiple candidates concurrently. The tree structure is constructed by taking the Cartesian product of the top predictions from each head. This attention mechanism considers tokens from the same continuation as historical data, and applies attention only on a token's predecessors. The tree structure allows processing numerous candidates simultaneously without expanding the batch size. Finally, we propose a self-distillation pipeline to generate a training dataset for MEDUSA heads that matches the output distribution of the model. A public seed dataset is used, and the model is used to generate responses to the prompts in the dataset. This self-distillation approach eliminates the need for an external training dataset and introduces almost no additional memory consumption. In conclusion, these techniques and algorithms improve the efficiency of LLM inference by reducing memory consumption, accelerating decoding steps, optimizing sampling schemes, and leveraging self-distillation for training.